Good morning to all. Today we are going to discuss about the dissociation energy. What is meant by dissociation energy? How it is calculating? The dissociation energy of two molecules. Okay. Dissociation energy of the electronic spectrum. Okay. What is meant by why this dissociation energy we are going to calculate by using of the not only the dissociation energy calculation, at the same time we are going to calculate the dissociation product also. Okay, dissociation product also. In this we are having ground state and upper state. The molecules are placed in the ground state. We are going to apply the any kind of energy automatically the moving of molecule into excited state. This is the basic principle for all the spectroscopy. First of all, we should know what is the principle of and basic criteria of the electronic spectroscopy. Definitely we should know. Okay. In then the case of dissociation energy, not only the dissociation energy and the dissociation product, at the same time of pre-dissociation. This kind of dissociation energy and dissociation product, calculation of diatomic molecule, particularly in electronic spectra, we are using by the Morse curve process. We are already discussed in the previous videos for Frank-Content principle. The Frank-Content principle, it have a 4 probability or there in the continuum and equal for or equilibrium and excitation equilibrium, and for 4 kind of probabilities there. Now we are going to calculating the dissociation energy and dissociation product of electronic spectroscopy. Okay. Some key point will now put some key points. Okay, see here. Okay, the point number 1, the amount of energy is required the amount of energy is required to breaking the molecule, required to break a stable molecule. Example, AB or XY in the ground state we put V is equal to 0 into 2 atoms, into 2 atoms like X and Y is known as dissociation energy. So consider X and Y molecule. We are putting the any kind of energy. For ground state will for X and Y. After the absorption of light or any kind of external energy, the molecules break down to form the X and Y. Okay, this is a dissociation energy. We are going to put the symbol as T0. This is a point number 1. Point number 2. Morse curve represents the dissociation equilibrium. What is meant by of? Dissociation equilibrium. The equilibrium is separated. We have for a upper state. Equilibrium is separated upper state and lower state. Equilibrium is separated of upper and lower state. We are going to represents the T0 double prime and T0 single prime. Okay. What is meant by this illustration dissociation of? First we are putting these one form graphical representation. This is the Morse curve representation. Okay. Okay. Zero, one, anywhere. V is equal to 0, 1, 2, 3. Okay. This is the ground, means a ground state. This is the upper state. Here also the 0, 1. Okay. This is of energy versus internuclear distance. Okay. This is located, you are going to put, this is the at upper ground state, you are representing the T0 double prime. Here we are going to representing the T0 single prime. Okay. This is the T0 single prime. The transition taking place for a upper state to any kind of this lower state to any kind of upper state. Okay. See, this is the level of this energy into internuclear distance. This parabola ending curve, this up to putting some layer using of, okay, this up to ground. This is the T0 double prime. Here also this is the T0 single prime. Okay, the overall and upper state to lower state, this point is E excitation. This is, we are putting the graph number A. What is the graph number A? Means the stable upper state. That is the stable upper state. Here automatically the transition in taking place V0 to any kind of this here. Okay, this another parabola curve. See, this is the energy. 0, 1, 2 and anyway. Okay. Taking place of, this is the upper state, this, okay, here up to here. This distance is E kinetics. Okay, this is the E kinetic way. This is the T0 single prime. This is a T0 double prime. Okay, that is the this distance is automatic for E excitation. This one, the dissociation point to here is the T0 double prime. Same one we are going to return as, this is the B, means a continuous upper state. This is the continuous upper state. Okay, these two diagram, it's going to explain about the dissociation energy of diatomic molecule. See here, this is the normal transition for stable upper state. This is the continuous state of this upper state. Okay, we are going to explain about now for a equation of graph A and graph B. From this graph, we obtained on a point is there, means this mu bar continuum limit is mu bar continuum limit is D0 double prime is a ground state plus E excitation, this is centimeter per minus 1. This is important one equation. Using of this equation, we are going to calculating the dissociation energy. Okay. Now, this from the 2 point means that from the two graph, the first one is the, see here, this is the stable upper state formula graph, another one is the continuum state. From in end of thermodynamical studies, first graph A, what kind of information we will get the graph A means, the thermodynamical studies often Firstly, thermodynamical studies often lead to an approximate value of T0 double prime, and hence T0 double prime with E excitation as accurately measurable spectroscopically. Okay, so we will get a rough value for E excitation is obtained. Okay, this is the first point, the thermodynamical studies. Okay, this is the first point of this graph. We are going to, what kind of information we will get? We are going to focusing the thermodynamical studies often is lead to an approximate value of T0, and hence approximate value is T0 will get. So in this equation, accurately measurable for spectroscopy, we will get the rough value of E excitation. Okay, and then of second point, the second point is okay, point number 2 for graph 1. Okay, we will get the E approximation value. So we are going to write this in the form of, we will get the rough E excitation value. So when the spectrum of spectrum of the atomic product studied, okay, as studied, okay, it is usually, so it is usually happens that only one, that is the important point, only one value of excitation energy corresponds at all well with E excitation. Okay, this is the we will get some information about graph A. Means under one of graph B, only the simple thing is from the second spectroscopic the dissociation is found. More than one dissociation, more than one dissociation limit as found. Okay, more than one dissociation is found. This is a very important point. In here only one graph A and graph E. What is the main difference? A is one dissociation, or it means it is the rough value of E excitation. But graph B we will get more than, this is a very important point, more than one dissociation point is found. Okay, that is the major difference of this graph A and graph B. Finally, we are going to apply these vibrational spectroscopy of Raman spectroscopy. The formula is mu is equal to this is V plus half mu excitation is minus, this is a harmonicity of this normal formula, V plus half squared excitation into Xe centimeter inverse. Okay, or otherwise we are going to write in the form of vibrational spectroscopy, that is V plus half omega bar E minus V plus half the whole squared omega E into Xe. Okay, normally the delta E means the value is the separation of E V plus 1 minus eta. V, that is the separation values. Okay. We are going to put the equation. This is equation number 1. That is equation number 2. Equation 2 represents the separation between neighboring levels. Separation level. Okay, this is 1 and 2. Okay. Finally, we will get, that is, it is equal to, you are going to put the equation number 1, equation 1 to equation 2 instead of delta E value or V max value, this dissociation limit value. Omega E bar minus 1 minus 2 into Xe into V plus 1 the centimeter inverse. The separation of the dissociation limit equal to 0 omega E 1 minus 2xe, the value V plus 1 or V max, that is V max means this continuum, the dissociation limit, plus 1 is equal to 0, or we are going to calculate the V max value, that is equal to 1 by 2xe minus 1. Okay, this is the way we are going to calculating the dissociation limit of this product of this diatomic molecule. Okay, first what is the dissociation point we should know. Okay, what is the dissociation point? That is the we are going to put the D0 value. Another one, the graphical representation, that is the stable point, stable one. Okay, another one is continuum point, graph A and graph B. Okay, that is graph A here, graph B. We will get information. This is the one or more limited dissociation point is there in this curve. See here, this mu continuum, this equation is important one. Okay, finally we are going to this calculation graph E for only one rough value of the point, but B will get the more than one dissociation point. This is the vibrational spectroscopy domain of the harmonic, this diatomic molecule formula, V plus half. Okay, V plus half and mu xe, otherwise we are going to write is in the form of V plus half mu xe minus mu plus half omega E and xe, X equilibrium formula. Finally we are going to delta E, that is equal to delta E is equal to delta E of V plus 1 minus EV. We are going to substitute the equation 1 into equation 2. What will happen? Omega E, this is the consolidated equation. We are going to calculate the dissociation limit, that is the V max value. Okay, these kind of information we will get the dissociation energy of diatomic molecule by using of Moscow. If you have any doubt in this video or in this session, please comment it. Thank you, and thank you very much for listeners and students. Please definitely like it or like the video and share the video. If you have any chemistry friends or that, you share it the video and like it also. Okay, thank you. இந்த வீடியோ பிடிச்சிருந்துச்சுன்னா லைக் பண்ணுங்கள், ஷேர் பண்ணுங்கள். Thank you very much.